Each new image captured by the James Webb Space Telescope offers another revelation, providing humankind with a fresh perspective on the universe that we've never seen before. Today marks an exciting new chapter in the exploration of our cosmos. This telescope represents one of humanity's greatest engineering achievements. The deeper we look, the less we understand. A concept that should define our study of cosmology, especially with the advent of the James Webb Space Telescope. The beginning of a new era in space science has arrived as the world gets its first look at the full potential of this incredible instrument. After more than 2 decades of planning, NASA launched its most expensive scientific mission ever. A $10 billion telescope designed to capture the faint starlight from the first galaxies formed in the fiery aftermath of the Big Bang. Despite various delays, the Webb telescope has finally delivered on its promises, and its latest images are sending shockwaves through the scientific community. These images challenge our entire understanding of galactic evolution, making us realize that we may need to rewrite textbooks about the universe's origins. Join us as we explore Webb's latest pictures, which suggest the existence of another universe at the edge of our own. According to the most widely accepted theory, the universe began about 13.8 billion years ago with the Big Bang. In its early moments, the laws of physics as we know them didn't apply. What would eventually become matter exploded outward in a fraction of a second, with the first particles like electrons, photons, neutrons, and protons forming the building blocks of our universe. These early seeds of stars, planets, and galaxies began to expand, creating a universe that became more homogeneous on a grand scale. This perfect uniformity meant that large-scale structures in the universe, like galaxies and clusters, were evenly distributed, like a 3D grid where one section wouldn't be significantly denser than another. In the first moments after the Big Bang, something called inflation is thought to have occurred. During this period, the tiny, packed universe expanded exponentially in a fraction of a second. This theory is still a cornerstone of the current model of the universe known as the lambda cold dark matter, lambda CDM, model. In this model, the universe is envisioned as a pipe, widening over time, though other models have also emerged based on observable data. Observational astronomy, which relies on the data that we can measure directly, is crucial for testing these theories and refining our understanding of the universe's future. One important piece of this puzzle is the cosmic microwave background, CMB, the faint radiation left over from the early universe. Radio telescopes can detect this radiation and convert it into a heat map that shows how matter was distributed roughly 400,000 years after the Big Bang. This map represents one of the first recognizable images of the universe before the formation of stars, planets, and galaxies. Just a nearly uniform sea of matter with slight variations that eventually led to the formation of the structures we see today. The CMB serves as evidence that the universe began in a much denser and hotter state, and has been expanding ever since. We can even estimate how fast this expansion is happening. Astronomers have long used the CMB to support the idea that the universe was once hot and has since cooled down. One way to test the accuracy of our models is to look at very distant galaxies, basically, looking back in time. The Hubble Space Telescope, for example, attempted to capture the earliest structures of the universe. In 1995, it spent 10 days capturing images of a seemingly empty patch of sky in the Hubble Deep Field. To everyone's astonishment, Hubble revealed thousands of galaxies at various stages of evolution, some much older than anyone had expected. In 2016, Hubble identified the farthest galaxy it had ever seen, called GN-Z11, which formed about 400 million years after the Big Bang. Although this was an early galaxy, its small size, only 1% of the Milky Way's mass, and solitary nature made it inconsistent with the predictions of the lambda CDM model. However, when the James Webb Space Telescope began operation, it completely changed our understanding of the universe. Launched in the summer of 2022, Webb's $10 billion investment has revealed galaxies forming much earlier than scientists had thought, and some of them are astonishingly large, brimming with stars. These findings have completely upended the scientific community, introducing a new reality where previous theories no longer seem to apply. The earliest and largest galaxies discovered by Webb appear to contradict prevailing ideas in cosmology, as they seem to be far larger than expected for their age. Many of these early galaxies are estimated to be more massive than the Milky Way, and some seem to have grown much faster than current models allow. This raises fundamental questions. Was the universe expanding faster in its early stages than we thought? Could this rapid growth have been driven by unknown forces or particles? Current models suggest that galaxies can only accumulate matter at a certain rate, and there is a limit to how fast material can be pulled into early galaxies. However, these new discoveries challenge that assumption, as these massive galaxies appear to have formed much more quickly than our theories allow, perhaps converting almost 100% of their gas into stars, which is theoretically near the limit of what's possible. This discovery is prompting some scientists to question whether standard cosmology is entirely accurate. Could we be missing something crucial in our understanding of how galaxies form and evolve? The next step will likely involve revisiting the theories of cosmic expansion and galaxy formation to incorporate these surprising new findings. In light of these revelations, the field of cosmology may be on the brink of a major shift, with new models and concepts emerging to explain these previously unseen phenomena. The James Webb Space Telescope has truly opened a new chapter in our quest to understand the universe, and its discoveries continue to rewrite the story of our cosmic origins. Despite decades of research and numerous analyses focused on directly discovering the particles that constitute dark matter, its nature remains elusive. Understanding dark matter is not just about solving a fundamental puzzle in physics, but also has significant implications for our comprehension of the universe's evolution and large-scale structure. For instance, the discrepancy between simulated predictions and observational data on the distribution of dark matter halos, such as the cusp versus core problem, illustrates the complexity of the issue. While simulations often predict dense, cuspy halos at the centers of galaxies, observations indicate a more spread-out, smoother distribution, particularly in smaller dwarf galaxies. Additionally, the missing satellite problem, where simulations overestimate the number of small satellites around large galaxies like the Milky Way, raises further questions about how dark matter interacts with baryonic matter, which includes ordinary matter such as stars, gas, and dust. Understanding how baryonic physics influences the formation and evolution of dark matter structures is essential to refining our cosmological models. Another major challenge arises from measurements of the Hubble constant, which describes the rate of the universe's expansion. Observations using various methods have yielded conflicting results. Local measurements, such as those using Cepheid variables, suggest a higher value for the Hubble constant compared to results obtained from the cosmic microwave background, CMB, by missions like Planck. This tension implies either flaws in our current understanding of cosmological parameters or systematic errors in measurement techniques that warrant further investigation. In addition to these observational challenges, the theoretical framework of the lambda cold dark matter, lambda CDM, model faces its own set of issues. The inclusion of a cosmological constant, lambda, to explain the accelerated expansion of the universe leads to the cosmological constant problem. Quantum field theory predicts an immensely higher value for lambda than what observations indicate, prompting physicists to confront this discrepancy. This disparity underscores our incomplete understanding of dark energy, the theoretical force responsible for the accelerated expansion of the universe. Moreover, the lambda CDM model's predictions for the large-scale structure of the universe often diverge from observed patterns at smaller scales, suggesting that further refinements to our cosmological models are needed. Understanding the formation and evolution of the universe requires a nuanced approach that integrates both dark matter dynamics and the complex processes of star formation and feedback mechanisms. The James Webb Space Telescope, JWST, with its extraordinary sensitivity and resolution, promises to shed new light on these processes. Building on the legacy of the Hubble Space Telescope, JWST's advanced capabilities allow astronomers to peer deeper into space, and further back in time than ever before. By studying the faint light from distant galaxies, JWST will unravel the mysteries of galaxy formation and evolution in the universe's early stages. Early observations from JWST have already challenged existing theories of galaxy formation. The discovery of massive galaxies dating back to only a few 100 million years after the Big Bang suggests that galaxy formation began much earlier than previously thought. These findings raise important questions about the conditions in the early universe and the processes that facilitated rapid star formation in these ancient galaxies. Furthermore, JWST's observations provide crucial insights into the long-term evolution of galaxies. By studying galaxies at different stages of their life cycle, astronomers can track the development of their structures, stellar populations, and star formation activities. These observations will refine models of galaxy formation and enhance our understanding of how galaxies like the Milky Way evolved over billions of years. In addition to galaxy evolution, JWST's observations contribute to our understanding of the cosmic microwave background, CMB. By studying the faint afterglow of the Big Bang, astronomers can probe the early conditions of the universe and test predictions from inflationary models. The precise measurements of the CMB provided by JWST will offer critical data to refine cosmological parameters and improve our understanding of the universe's origins and evolution. While the Lambda CDM model has provided a solid framework for understanding the large-scale structure and evolution of the universe, ongoing observations and theoretical challenges encourage researchers to refine and expand our cosmological models. The launch of the James Webb Space Telescope marks a groundbreaking moment in astrophysics, offering unprecedented opportunities to explore the universe with exceptional sensitivity and resolution. As JWST continues to unveil the hidden secrets of the cosmos, it promises to revolutionize our understanding of the universe's grand history and inspire future generations of astronomers to push the boundaries of human knowledge. The Big Bang Theory, which explains the beginning of our universe, has led to speculation about new laws of material science, such as a potential early form of dark energy or new physical phenomena. Some theories even suggest that the universe might have been born with incredibly massive black holes, or that a novel, seemingly eternal particle might have decayed into regular matter over time. While many dismiss these ideas as absurd, it's important to recognize that even before the launch of the James Webb Space Telescope, several issues had already arisen with our current cosmological model. The nature of dark matter. One of the key challenges with the Lambda CDM model, the standard model of cosmology, is the nature of dark matter. Although dark matter has not been directly observed, its existence is inferred through its gravitational effects on visible matter and the cosmic microwave background. Despite various detection methods, including direct and indirect observation techniques and galactic surveys, the particles that make up dark matter remain unidentified. Dark energy and the cosmological constant. Another contentious aspect of the LCDM model is the introduction of a cosmological constant, lambda, to explain the accelerated expansion of the universe. Originally proposed by Einstein and later discarded, lambda was reintroduced in the late 1990s when observational data suggested a speeding up expansion. The challenge lies in reconciling the small value of lambda predicted by quantum field theory with the observed energy density of dark energy, leading to the cosmological constant problem. Structure formation and simulations. While the LCDM model successfully predicts the large-scale structure of the universe and the distribution of galaxies, problems arise at smaller scales. For example, simulations often predict more satellite galaxies around large galaxies like the Milky Way than are actually observed, an issue known as the missing satellite problem. This suggests that either our understanding of dark matter is incomplete, or that simulations need refinement, such as incorporating baryonic, normal, matter more accurately. The cusp versus core problem. Another issue within the LCDM framework is the discrepancy between predicted and observed density profiles of dark matter halos. Simulations tend to predict a cuspy density profile in the centers of dark matter halos, while observations of dwarf galaxies and other structures suggest a more cored profile. This discrepancy raises questions about the effects of baryonic feedback processes, like supernovae and black hole growth, on dark matter distribution, which are not yet fully understood or included in current simulations. Hubble constant tension. Recent measurements of the Hubble constant, which describes the rate of expansion of the universe, have revealed a persistent tension between values derived from local measurements, using objects like Cepheid variables, and those obtained from the cosmic microwave background. This discrepancy hints at potential flaws in our cosmological models, including the LCDM model, or the possibility of unresolved systematic errors in measurements. Beyond these specific challenges, the LCDM model also leaves some significant questions unanswered. For example, it does not fully explain the nature of inflation, the rapid expansion of the universe in its early moments. While the LCDM model remains robust in many respects, it continues to face scrutiny and challenges from both new observational data and theoretical inconsistencies. One of the greatest mysteries in modern cosmology revolves around the elusive nature of dark matter, an invisible substance inferred through its gravitational effects on visible matter and the cosmic microwave background.